Welcome. Today we are going to talk about how we solve a system of 3 or more linear equations using matrices. In our last lesson, we saw how painful it can be to use the various steps and calculations to solve a system, which is fantastic to know how to do because you won't always have technology around to help you. But if you have access to a calculator, or if you have a graphing calculator available online, then this is an alternative method. The nice thing about using matrices to solve systems of equations is that it scales. So you could solve systems of 5 equations, systems of 10 equations, and a matrix, the matrices will lend itself very easily to that, where doing it by hand becomes almost impossible to do accurately. All right, so some things, hopefully you've already seen the video that introduced you to what a matrix was and how they can be manipulated. What's important to know here is that we can actually write a system of equations as matrices. So we would use A, matrix A would represent the coefficients of all of the variables in your system of equations. And then we have the actual matrix that houses just the variables, and that will be equal to the constants in your equation. So one important note here is that you would always need to have your linear equations in standard form in order to be able to use matrix operations on them. So a system can be multiplied by using the inverse of matrix A. There's lots that I'm glossing over. You can do Gaussian elimination. You can do all sorts of identity matrices work. There's a lot of matrix work that I am simply skipping. I'm sort of cutting to the chase and getting to the easy part here, or the lesson to be learned. The rest of that good stuff you will learn in pre-cal. All right, so I basically am going to use an inverse, just like if I had the equation 2a equals 6, I multiply by the inverse of 2, and the inverse of 2, where its identity is 1/2, and if I multiply both sides by 1/2, then the resultant, these two, form 1, which is why y 1/2 is called the identity, or it's the inverse, because it undoes whatever's going on here. 1a equals 3. And so that's a super simplistic example of what's going on here, but what we're going to learn is that if we multiply both sides of this equation by the inverse of matrix A, which is noted by a little -1, just like we do all inverses. And so if I multiply both sides of this equation by the inverse, these essentially cancel each other out, and I'm left with my variables are equal to the inverse of A times matrix B, and this typically will end up being a nice friendly matrix that gives you the answers to your X, your Y, and your Z. That probably makes no sense whatsoever. So let's look at the steps, and then we're going to do some. So the first thing, like I said, is we need to make sure that our equations are in standard form. And in case you've forgotten what standard form of a linear equation is, we wrote it out here. We need to place all of the coefficients, which, if you remember, those are just the numbers that are in front of the variables. All of the coefficients are going to go in a 3x3 matrix. Why 3x3? Because I have 3 equations and I have 3 unknowns. The next thing we're going to do is we are going to put all of our variables in a separate matrix, because that's essentially what we're solving for, if you want to think of it that way. And then the last thing we're going to do is we're going to take the constants from each equation and put them in the matrix. When we multiply both sides of our equation by the inverse of matrix A, we will end up isolating our variable matrix, and the multiplication that we do there for the other side of the equation will result in our answers, if you will. All right, so let's try this. The first thing I'm going to do is I'm going to put all my coefficients into a matrix. I'm going to start 3, -4, 2. I like writing it out. If there's no number in front of your variable, remember that's a 1. Math people are too efficient to write it. Notice I didn't say lazy. Okay, so now I have a 3x3 matrix that houses my coefficients. I'm going to put my variables in the next one. I like doing this just so I can use it as a reference point later. And then the last thing I'm going to do is I'm going to take my constants, which are these fellas, and I'm going to put them into their own matrix. And then one thing you'll learn in pre-calculus is how to find the identity matrix for this, and you'll be able to do all of this through calculation by hand. I'm not about that life this year, not at this time. So what I'm going to do is I'm going to use my calculator and my matrix, my use of matrices to help me solve this. And because I knew this was coming, I preloaded, let's scoot, always look at the best way to show you this. I preloaded matrix A, which is where I stored this one, and I stored this one as matrix B. I preloaded them into my calculator, so if I wanted to, I could do second matrix. That's not second matrix, second matrix. And you'll notice I have a 3 by 3. If I want to, I can just check, and it should be the same as this one. I can check matrix B as well, and it represents my constants. So now, easy schmeezy, what I want to do is I want to do that multiplication where I multiply both sides by the inverse, and what I'm actually going to do looks just like this. That's what it's going to look like when I type it into my calculator. So I'm going to start by finding matrix A, and then I'm going to take the inverse of it, and I'm going to use my inverse key, which is the -1. And all that does, you'll notice, is just put the little -1 to indicate that it's going to take the inverse of matrix A. And I'm going to multiply that by matrix B. And you can use a multiplication sign, but you do not have to. But what you see in this window should mimic this sort of formula, if you will, right here. And then when I hit enter, it solves the system of equations for me. I'm going to put my resulting answers into my answer matrix, 2, -1, 4. And what that's telling me, folks, is that x equals 2, y equals -1, and z equals 4. And while it might be a bit of a pain to put these two matrices into your calculator, I'm 100% sure that all of you will agree that solving a system of 3 equations using matrices is infinitely easier than solving it by hand. Make sure that you have entered your matrices correctly, and don't forget that order matters when using multiplication of matrices, and that you need to take the inverse of A times B. If you do those things, this should be a walk in the park. Example 2 is another system of equations that you can solve using matrix operations. The only difference here is that some of the variables are just not even present in these equations, and they are also not written in standard form. So they need to be rewritten in standard form. You can see even I make mistakes here. So I rewrote them in standard form, and now I can create my 3 matrices that I need and use matrix multiplication using the inverse of A times B to come up with the solutions. Go ahead and pause the video and try that now. All right, here's what I came up with. This is my coefficient matrix, my variable matrix, and my constant matrix. And when I multiply, and I'll even write it out, I multiplied the inverse of A, or whatever you name your matrix, times the inverse of my second matrix, and that's where I came up with x is 7, y is 14, and z is 15. Let's see if we can solve an application problem using these. All right, folks. There's my problem. Let's start by reading the problem. Vista Ridge High School is ordering more technology equipment. Laptops cost $715 each, tablets $410, and cell phones $245. Small segue. Like any school orders cell phones. We're going to go with it. They purchased 25 times more tablets than cell phones. The district spends a total of $250,350 on 486 devices. How many of each device did they purchase? There's kind of a lot of things going on here. First thing I did was identify the 3 types of purchases they made, and I used mnemonic variables because that helps my brain. The next thing I'm going to do is I'm going to need to write my three equations. As we've talked about before, one kind of information that I can glean is my value, and that's how much each device is worth. Those can be indicated by the dollar sign. There's another one over here. So I know that if I buy all of these things at their different prices, then it's going to add up to this number. So I'm just going to start off. That's usually a good place to start. I'm going to do 215 laptops, plus I'm going to add to that 410 tablets. I'm going to add to that $245 for each cell phone. I think I said that one wrong, but anyway. And then all of that together should add up to this really, to me, huge number. Like, you could buy a really nice house for that number. Anyway. Okay, so I have one of the three equations that I need. The next thing I notice is that they tell me that there are 25 times more tablets than cell phones. Notice there's no is in this statement. So there's no, I'm not saying that 25 times the tablets plus cell phones or anything like that. There's just simply more of these than there are of the cell phones. So in order to make them equitable, I am going to take the number of cell phones and I'm going to multiply it by 25, because if I take the number of cell phones times 25, then it should now be equal to the number of tablets. That equation is not in standard form, and it has absolutely nothing to do with laptops. So I need to rewrite it in standard form, which I'm going to take a moment and do. And that would be 0 laptops. And that would be a minus 1 tablet is going to be, plus the 25 cell phones. And because I'm subtracting t from both sides now, my right side is just 0. So that's in standard form. And it matches the order of my variables up here. One reason that color is nice. And then lastly, there's another number that I haven't used, and that number is my, the total number of devices. So this is my counting number. So all my purchases should result in 486 boxes of laptops, plus my tablets, plus my cell phones, and all of those should add up to 486. Okay, so now I'm ready to write a matrix using my three equations. If I write them all out, and I'm just gonna pay no heed to the color, it means nothing anymore. I'm being consistent with our previous problems. 25, ooh, I lied. This is 0, this is -1, and this is the 25. See, I started putting that one in instead of my standard form. And this is just 1, 1, and 1. Make sure that's nicely scribbled out. My variable matrix is going to be my laptops, because I put that number in first, then my tablets, and then my cell phones. And lastly, I'm putting in my constants, 250, 350, 0, and 486. If I were doing this by hand, this would be a bear of a system to solve, because it involves some rather large numbers. So I'm grateful that I have a matrix that I can use instead. And what I'm going to do is I'm going to say that this matrix right here is going to be the result of the inverse of A times B. And that should give me the value of my laptops, my tablets, and my cell phones. All right, so being an efficiency expert, nothing to do with being lazy, I went ahead and put these matrices into my calculator ahead of time. So you can just verify that I've typed it in correctly. One of the biggest mistakes students make is forgetting the negative sign in these matrices. And that's a pretty common problem. But once I know and have verified that they're incorrectly, then I will take I'm going to take my matrix A, take the inverse by typing that inverse button, and then I'm going to multiply it by matrix B. And so again, what you see on your screen here should mimic this formula. And when I hit enter, it does all the work for me. It's so exciting. Okay, so that tells me that there are going to be 700 and, let's see, here we go. 715 laptops, 300 tablets, and 12 cell phones. I would not want to just leave it like this and assume my teacher read my hieroglyphics. I'm going to label my answers so that there is no ambiguity. Unless, of course, my pen decides to run out of ink. But you get the drift. That's it, folks. That's how we can use matrices to make our lives infinitely easier when solving systems of equations. Good luck with this, and I'll see you next time.